Okay, good afternoon students. We will start the session. So in the last class we have discussed about drift current, diffusion currents and different current components in the PN junction diode, right? So what is the drift current? So drift current means, see here, what is the difference between drift current and diffusion current? So drift current is the flow of electric current due to motion of charge carriers, right? So due to the motion of charge carriers, either electrons or holes, due to the motion of either electrons or holes, the drift current is flowing through the diode and applying the external electric field. Okay, so the drift current is the flow of electric current. It is the flow of electric current due to motion of charge carriers and applying external electric field. Okay, so due to the motion of charge carriers, the current is flowing with the external electric field. That current is called drift current. Okay, so if you see the diffusion current, so here higher concentration region, see here it is the higher concentration region and it is the lower concentration region. Here the charge carriers are moving from higher concentration region to lower concentration region, right? See here it is the higher concentration region and this one is the lower concentration region. Here the charge carriers are moving from higher concentration region to lower concentration region, right? So what is diffusion current? The movement of charge carriers of same type takes place from a region of higher concentration to lower concentration. So that current is called as diffusion current. Okay, so here the charge carriers are moving from higher concentration region to lower concentration region. So the current due to this movement of charge carriers is called diffusion current. So that is the diffusion current. Okay, so total current will be, the total current in a semiconductor is, it is the addition of both the drift current and diffusion currents. Okay, so for n type we can write like this, see here. So for n type semiconductor, so drift current is this one, nq mu n into E, plus diffusion current is q dn into dn by dx. So where capital it is diffusion constant, this one is the dn by dx is the concentration gradient, right? So in n type material. So whereas in p type material, so this we can write the total current can be write, so Jp equal to, this is the current density, so pq mu p into E minus q dp by dx. It is the combination of drift current and this one is the diffusion current. Okay, it is the total current in the PN junction diode. We have seen about law of electrical neutrality. So it is n plus Na equal to, see here, n plus Na equal to P plus Nd. So law of electrical neutrality states that the total positive charge is equal to the total negative charge. Okay, so if we see the current components in a PN junction diode, see here it is a p type and this one is the n type materials. So the current components in a PN junction diode, so here IPP it is the whole current in p type material. Okay, so IPP it is the whole current in the p type material and INP is the electron current in the p type material. So INP is the electron current in the p type material. So here the minority carrier current, so the minority carrier current is due to flow of minority charge carriers. The minority carrier current is due to the flow of minority charge carriers, right? So in the p type material the electrons are minority carriers. So that's why, so I and P, it is the electron current in the p-type material, that is the minority carrier current. Whereas in n-type material, so here we are having two currents, one is I and N, that is the electron current. So electron current in the n-type material, and IPN is the whole current in the n-type material. Clear? So IPN is the whole current in the n-type material. So these are the current components in PN junction diode. So in p-type material, we are having this IPP and INP. In the n-type material, we are having INN and IPN. So majority carrier current and minority carrier current. So due to the flow of majority carriers, the majority carrier current is flowing through the diode. So that is INN, here it is electron current, and IPP is the whole current. Okay, here the number of, so these inducted minority carriers falls off exponentially with the distance from the junction. So here, see here, so the minority carrier current, it falls exponentially, right? So the minority carrier current, so falls exponentially with the distance from the junction. See here, there are two minority carrier currents, IPN of X and INP of X. Okay, so all these things we have discussed in the last class. Today, so we will discuss about energy band diagram for open circuited PN junction. Energy band diagram for open circuited PN junction. Okay. So here, when the P and N-type semiconductors are connected, the Fermi level must be constant throughout the specimen at equilibrium. See here. So energy band diagram. So it is P region. See here, it is a P region and it is a N region, right? So this one is conduction band and this one is valency band. Here in the N region, it is the conduction band and it is the valency band. Here this line represents the Fermi level, EF. Okay, so EF, this line represents the Fermi level. So here, see here, this one is ECP, and this one is EVP. Okay, so it is the conduction band energy level in P region. Conduction band energy level in P region. This one is the valency band energy level in the P region. Here it is ECN and EVN. So conduction band energy level in N region and conduction band, valency band energy level in N region. Okay. So between these two, P region and N region, so it will be a space charge region. Okay. So we know that what is space charge region. See here, from ECP to EVP, this gap is from ECP to EVP. So that is EG, right? So from this point to this point, it is EG by 2, and from this point to this point, it is EG by 2, right? So from ECP to EVP, we can write EG. So 1 by 2 EG plus 1 by 2 EG. So that is the energy gap. Okay, energy gap. It is the gap between conduction band and valency band. Okay. So this level is the Fermi level. This level is the Fermi level. See here, this portion is E1 and this portion is E2. So from this point to this point, it is E2, and from this point to this point, it is E1. So from here to here, it is potential E0. Okay, potential E0. So here we need to calculate E0. Here we need to calculate E0. So see, here is the conduction band and it is a valency band in the P region, and it is the conduction band and it is a valency band in the N region. So forward biasing increases the electron density in the conduction band of the n side. So that's why the Fermi level moves upwards. See here, the forward biasing increases the electron density in the conduction band. The forward biasing increases the electron density in the conduction band of the n side. So that's why the Fermi level moves upwards. The Fermi level moves upwards in the n region. So similarly, due to the increase in the hole density in the valency band of the p type, the Fermi level moves downwards. See here, the Fermi level, it is nearer to valency band, but here in n region the Fermi level is nearer to conduction band. Clear? So here the Fermi level is nearer to valency band, here the Fermi level is nearer to conduction band. So because the forward biasing increases the electron density in the conduction band of the n side. So due to this, the Fermi level moves upwards, that is in the n region, whereas in the p region, so here due to increase in the hole density in the valency band of the p side, the Fermi level moves downwards. Okay, the Fermi level moves downwards. Here we need to calculate this potential E naught. See here, from the from this figure, the Fermi level is close to the valency band in p type and close to the conduction band in n type, right? So here E naught equal to ECP minus ECN. One second. So see this diagram. One second. Okay, see this one. So here E naught equal to ECP minus ECN. Okay, so E naught equal to this level is ECP means this level, ECP minus ECN, ECP minus ECN. Okay, so that is E naught. So this we can write EVP minus EVN. EVP minus EVN. Okay, so here E naught equal to, so this ECP minus ECN, that means this level, right? So ECP minus ECN, that is equal to EVP, this level, EVP minus EVN. Okay, so this we can write E naught equal to E1 plus E2. So E naught is, it is the energy ranges from these two levels. So we can write E naught equal to E1 plus E2. So E1 is, so this range is E1 and this range is E2. So E naught equal to E1 plus E2, right? So E naught equal to E1 plus E2. So from this figure we can write EF minus EVP equal to, see here, EF minus EVP. So this gap, EF minus EVP equal to, so EG by 2. So this total gap is, it is, so from this point to this point it is EG by 2, right? So EG by 2. So actually we required this level. We required this level, that is EF minus EVP. Here we required EF minus EVP, that is equal to EG by 2. Okay, this gap. So e point nunchi e point variki, that is EG by 2. So ikkada E1 minus chesavu anukondi. So EG by 2 minus E1 equal to EF minus EVP, ఈ గ్యాప్ వస్తుంది రైట్. సో ఈ టోటల్, సో ఈ గ్యాప్లోంచి మనం దీన్ని మైనస్ చేస్తే సో మనకు వచ్చింది అంటే ఇంకా EF మైనస్ EVP. ఓకే, సో దట్ ఈస్ we can write EF minus EVP equal to EG/2 minus E1. Similarly, ECN minus EF equal to, see here ECN. So ECN minus EF equal to, so this gap, right? So ECN minus EF equal to, we can write EG/2 minus E2. So it is the EG/2. Okay, it is EG/2. So EG/2 minus E2. Clear? So from this we can write EF minus EVP equal to EG/2 minus E1. So here we can write ECN minus EF equal to EG/2 minus E2. Okay, so they are the two equations. So from these two equations we can write E0 equal to E1 plus E2. E0 equal to E1 plus E2. See here. So if we check the diagram, then it is easy to understand. So what we have discussed right now. So it is EF minus EVP equal to EG/2 minus E1, and ECN minus EF equal to EG/2 minus E2. Okay, so from these two equations we can write, so E0 equal to, so from these two equations we can write E0 equal to E1 plus E2, that is equal to, so EG minus ECN minus EF minus EF minus EVP. Okay, so that is the equation 4. See here. So we know from law of mass action, NP equal to Ni square, right? So we know this equation, NP equal to Ni square, and here N equal to, so we know NC into e power minus of EC minus EF by KT, and P equal to NV into e power minus of EF minus EV by KT. Okay, so from these two equations, N and P, so multiply these two equations. So NP equal, that is this one, NC into e power minus of EC minus EF by KT. Similarly NV into e power minus of EF minus EV by KT, right? So take NC NV, so we can write NP equal to NC NV into e power minus of EC minus EV by KT, right? So that is, so NP, right? Okay, so here in place of NP we can substitute this one, NC NV into e power minus EG by KT. So NP equal to Ni square, right? So from this equation we can write EG equal to, so from this equation we can write EG equal to KT ln of this one, NC NV by Ni square. Okay, so EG equal to KT ln of NC NV by Ni square. Now how to calculate ECN minus EF? How to calculate ECN minus, from the diagram, how to calculate ECN minus EF? So for n-type semiconductor, so we know that Nn equal to Nc into e power minus ECN minus EF by KT. Here this we can write, so it is equal to Nd. So in place of Nn we can write Nd equal to Nc into e power minus of ECN minus EF by KT, right? So from this equation we can write ECN. So ECN equal to, sorry, ECN minus EF. So we required this one, ECN minus EF. So ECN minus EF equal to KT ln of NC by ND. Okay. So finally we need to calculate E0, that is equal to E1 plus E2. Next, calculation of EF minus EVP. So from the diagram, so how to calculate EF minus EVP? So here, so for p-type semiconductor, we can write, so PP equal to NV into e power minus of EF minus EVP by KT. So you need to remember some equations in n-type semiconductor and in p-type semiconductor, right? So this we can write NP equal to NA, sorry, PP equal to NA. So from this we can write NA equal to NV into e power minus of EF minus EVP by KT. So from this equation we can write this one, EF minus EVP equal to KT ln of this one, NV by NA. KT ln of NV by NA. Okay. So we got ECN minus EF and EF minus EVP. So substituting ECN minus EF and EF minus EVP in the E0 equation. So in the first equation, right? So if you substitute, so substituting all these equations in equation 4, so it is equation 4 is E0 equal to this one, E1 plus E2, that is equal to EG minus ECN minus EF minus of EF minus EVP. Clear? So if you substitute ECN minus EF and EF minus EVP, then you will get E0 equal to KT ln of this one, NC NV by NI square minus KT ln of NC by ND minus KT ln of NV by NA. Okay. So after solving, we get E0 equal to KT ln of NA ND by NI square. So E0 equal to KT ln of NA ND by NI square. Okay. So just check the diagram. What we have calculated. Okay. So here in this diagram we need to calculate E0. So finally in this diagram we need to calculate this E0. Okay. So here once again I am explaining. So E0 equal to, E0 equal to E1 plus E2. So it is E1 and it is E2. So we can write E0 equal to E1 plus E2. E0 equal to E1 plus E2, right? So how to calculate E1? So E1 equal to this one, ECP minus ECN, right? ECP minus ECN. So similarly E2 equal to EVP minus EVN. So EVP minus EVN, right? So E0 equal to, we can write E1 plus E2. So from law of mass action, we know that NP equal to Ni square. Okay. So from NP equal to one second. So from the figure we can write EF minus EVP equal to EG by 2 minus E1 and ECN minus EF equal to EG by 2 minus E2. So see these two equations from the figure. So EF minus EVP, right? So it is EF minus EVP means this level. It is the EF level. This one is EVP. So we required this level. So EF minus EVP equal to, how to write? This one is EG by 2. This total gap is, so from here to here, from this point to this point, it is EG by 2, right? So subtract E1 from EG by 2. So subtract this E1 from EG by 2, then you will get EF minus EVP, right? So then you will get this gap. So subtract this EG by 2. So subtract this E1 from EG by 2. Then you will get EF minus EVP. So similarly, ECN minus EF equal to EG by 2 minus E2, right? So from law of mass action, we can add NP equal to Ni square, and we know N equal to Nc into e power minus of Ec minus Ef by Kt, and P equal to Nv into e power minus of Ef minus Ev by Kt, and substitute these two in this equation. Then here Np equal to, we will get Nc Nv into e power minus Eg by Kt. Okay. So and calculate ECN minus EF, and calculate EF minus EVP, and substitute, so this ECN minus EF and EF minus EVP in, so first equation, E0 equal to E1 plus E2, right? So finally you will get E0 equal to KT ln of Na Nd by Ni square, and we know that V0 equal to Q into V0, Q into V0. So here from this V0 equal to KT by Q, right? So KT by Q into ln of Na Nd by Ni square. So it is the final equation. E0 is the final equation. So E0 equal to KT ln of Na Nd by Ni square. Acceptor concentration, donor concentration, these two terms, right? So next we will see what is the forward resistance and reverse resistance. What is forward resistance and reverse resistance? So what is the static resistance and dynamic resistance? One second. Okay, there are two resistance. One is dynamic resistance or DC resistance, and second one is static resistance or AC resistance. Okay. So there are two diode resistances. First one is dynamic or DC resistance. Dynamic or DC resistance. Second is static resistance or AC resistance. Okay. So how to define static resistance, how to define dynamic resistance in forward bias and in reverse bias, in both forward bias and in reverse bias. See here, so the static resistance equal to, so in forward bias, how to calculate static resistance? It is the ratio of forward voltage to forward current. It is the ratio of forward voltage to forward current. Okay, in forward biased condition, it is the ratio of forward voltage to forward current. That is called static resistance or DC resistance. So how to calculate dynamic resistance or AC resistance? Here in forward bias, the change in forward voltage to the change in forward current. The change in forward voltage to the change in forward current. Here delta represents change in. Okay, so in forward bias we are having this both static and dynamic resistance. So static resistance is defined as the ratio of the ratio of forward voltage to forward current, or the dynamic resistance is defined as the ratio of change in forward voltage to change in forward current. Change in forward voltage to change in forward current, right? So in reverse bias also, the static resistance is the ratio of change in reverse voltage to it is the ratio of reverse voltage to reverse current, right? Here the VR is the reverse voltage and IR is the reverse current. So the static resistance is VR by IR. Static resistance is VR by IR. Similarly, the dynamic resistance is delta VR by delta IR. That is in reverse biased condition. Okay. So it is about diode resistances. So we are having two resistance, static resistance or DC resistance, and the second one is dynamic resistance or AC resistance. So in the forward bias, the static resistance is the ratio of forward voltage to forward current, and the dynamic resistance is the ratio of change in forward voltage to change in forward current. Similarly, in the reverse bias, the static resistance is the ratio of reverse voltage to reverse current, and the dynamic resistance is the ratio of change in reverse voltage to change in reverse current, right? So it is about diode resistances in forward bias and reverse biased conditions. So with this I am going to stop the presentation. So tomorrow we will discuss about diode current equation.